Hi and welcome to another video. Today we're going to look at an introduction to electrochemistry. So we're really going to look at what is electrochemistry about and how does this actually relate to redox reactions. So when we have a redox reaction, we describe a redox reaction in terms of a transfer of electrons. One species is gaining electrons, that's the thing that's being reduced, and the other thing is losing electrons, the thing that's being oxidized. So electrons are moving from the thing that's being oxidized to the thing that's being reduced. And we've talked about this a lot. It's kind of one of those basic principles that you should all know by now. But in fact, has anybody ever provided you any proof that this is what's actually happening? How do we know? Where is the evidence? And that's where electrochemistry comes into it. You see, those of you who take physics hopefully will recognize that when we talk about electrons being lost and electrons being gained, and electrons moving particularly, actually the movement of electrons is what we call electricity. And the movement of electrons is current, and the energy carried by those electrons is the voltage or potential difference. So, in theory, if something is losing electrons and something is gaining electrons, we should be able to make those electrons move in such a way that we can actually measure the fact that they're moving. In other words, we should be able to measure an electric current. However, at the moment, when we do a redox reaction in a beaker, it typically happens in a confined space where the atoms that are being oxidized and being reduced are directly contacting each other. So it's very hard to set up a circuit around it. So what we need to do is we use what we call an electrochemical cell. And an electrochemical cell is one where we have separated the oxidation and the reduction processes into two separate spaces, effectively. And we connect those up by a wire so that the electrons will have to move through the wire to get from one species to another. So when something is being oxidized and it's losing electrons, then the electrons have to travel through a wire to get to the thing that's being reduced, which is therefore gaining the electrons. Now that is not a complete circuit, so we need a salt bridge to keep everything neutral. Now, of course, all these words are quite random at the moment. So let me show you what I mean in terms of a diagram. We're going to make one of these in class as well. Actually, we're probably going to make several in class. But if we have a look at this diagram, you can see that in the left-hand side, in this beaker, if you will, I have a solution of zinc sulfate and a piece of zinc. On the other side, I have a solution of copper sulfate and a solution of copper. And what happens is that the zinc is oxidized and the copper is reduced. Now this is exactly the same reaction that would happen if I took a piece of zinc and dunked it in a beaker of copper sulfate. I would get copper plating around my zinc and the color in the copper sulfate would become more pale, while the piece of zinc actually got smaller. All we've done here is we've separated them out into two pieces. So in the left-hand beaker, we've got the zinc and the zinc sulfate, which is zinc 2+. And in the right-hand side, we've got the copper 2+ and the copper metal. And so what happens is in the left-hand beaker, the zinc is being oxidized to form zinc ions. So that zinc will very slowly dissolve. And as it does that, of course, it produces electrons. Those electrons travel via the wire into the piece of copper metal. Because there are electrons building up on that electrode, the pieces of metal are known as electrodes, then the copper 2+ ions in the solution are then attracted to that electrode, which is providing the electrons, where the copper 2+ ions and the electrons come together to make more copper metal. Now, you'll see what's labelled as a KCl salt bridge through the middle. And what that does, of course, as we're creating zinc 2+ in the left-hand side left-hand beaker is the salt bridge will provide some extra negative ions in that solution so that it stays neutral. Similarly, on the right-hand side, we're getting rid of copper 2+ ions, so that solution would probably be getting more negative. So the salt bridge provides those negative ions, positive ions, to replace the ones that are being lost. You can put a voltmeter onto the wire. You can also put light bulbs or any other thing on there. This is the basic principle of how all batteries work. They have one thing that's being oxidized, one thing that's being reduced, and the electrons are flowing from one thing to the other, and we can harness the energy of those electrons along the way. So this is everything from the little button battery in your watch to the lithium-ion battery in your cell phone and everything in between. These electrochemical cells are incredibly important. Now, there's a few little terms to note in here, and I'll go through these in more detail in another video because this is really just an introduction. But the two pieces of metal in there are known as electrodes. We have an anode and a cathode. And an anode is where oxidation occurs, and a cathode is where reduction occurs. And those are some really important terms to remember. And we have a salt bridge between them. Now, just for a little bit of fun and to help you remember this, when you finish watching this video, I would really love it if you jump onto YouTube, well, you'll already be on YouTube, and find this video. It's called You Start at the Anode, and have a listen to it. I'm not going to apologize. It's kind of irritating, but the chemistry in it is fabulous, and it will really help you to remember these key concepts. Okay, so that's all I've got for you today. Next lesson we will get into the kind of guts of how it works, but first when we get to class I will do some demos of how these things actually work and what they really look like. Okay, thanks for your time, girls, and I will see you in class soon.